Why is the sky blue? It is perhaps the most iconic kid question in history. It sits right at the top of the curiosity leaderboard, alongside why is grass green? And how do planes stay in the air? But if you take a second and ask the average adult on the street this question, you usually get a very confident, I have absolutely no idea. Or even more likely, you get an answer that sounds smart, but is scientifically total nonsense. We grow up looking at this giant blue dome every single day of our lives, yet most of us go to our graves without actually knowing why it looks the way it does. The most common lie people tell, and you've probably heard this one in elementary school, is that the sky is blue because it reflects the ocean. It sounds poetic, it's easy to remember, and it sounds vaguely logical because the ocean is also blue. But it is completely 100% wrong. If the sky were simply a mirror for the ocean, the sky over the Sahara Desert or the middle of Kansas would be beige or green. Spoilers, it isn't. The sky is blue in the middle of a landlocked continent just as much as it is over the Pacific. In fact, it's actually the other way around. The ocean is often blue because it is reflecting the sky. Another popular theory is that the air itself is just naturally blue, like a giant bucket of blue paint was dumped into the atmosphere. People imagine that if you could just grab a handful of air and squash it together, it would eventually look like blue jello. But air is transparent. If you put air in a glass jar, it doesn't turn blue. If you look at the air in your living room, it isn't blue. To find the real culprit behind our colorful ceiling, we have to look 93 million miles away at a giant, screaming ball of fusion, the sun. To understand the sky, we first have to understand sunlight. Sunlight looks white to us, but white is a bit of a scam. White light is actually a chaotic mosh pit of every color in the rainbow all crammed together. You can prove this yourself with a simple glass prism. When you pass sunlight through a prism, the different colors bend at different angles, revealing the secret hidden inside: red, orange, yellow, green, blue, indigo, and violet. This is the visible spectrum, and each of these colors is actually a wave of energy. However, not all waves are created equal. Think of red light as a long, lazy wave. It has the longest wavelength in the visible spectrum, which means it's the chill color. Red light waves are like heavy-duty off-road trucks. They can roll over small bumps without much trouble. On the other end of the spectrum, you have blue and violet light. These are high-energy, short, frantic waves. They are vibrating much faster and have a much shorter wavelength. If red is a heavy truck, blue is a tiny, high-speed bouncy ball. Now let's look at the obstacle course these waves have to navigate. Our atmosphere isn't just empty space. It's a thick soup made of trillions upon trillions of gas molecules and tiny particles. Most of this is nitrogen and oxygen. As sunlight enters the atmosphere, it runs into these molecules like a bouncer at a crowded club. This is where the physics gets interesting. Because red light has such a long, lazy wave, it mostly passes right through these gas molecules without hitting anything. The molecules are simply too small to interfere with the long red waves. It's like a tall person walking through a crowd of toddlers. They just breeze right through the chaos without being diverted. But blue light is a different story. Because its wavelength is so short and frantic, it is almost exactly the right size to get tripped up by nitrogen and oxygen molecules. When a high-energy blue wave hits a gas molecule, it doesn't pass through. Instead, the molecule absorbs the energy and then immediately radiates it back out in every single direction. This physical phenomenon is called Rayleigh scattering, named after Lord Rayleigh, the British physicist who figured this out in the 1870s. Imagine throwing a blue ball at a metal pole and watching it shatter into 1,000 tiny blue sparks that fly off in every direction. This is happening trillions of times every second, all across the upper atmosphere. When you look up at any part of the sky that isn't directly at the sun, your eyes are catching these scattered blue waves that have been bounced around like pinballs until they finally hit your retina. The sky isn't a solid blue object, it's a giant glowing fog of scattered blue light. But if the atmosphere is scattering light, why is the sunset red? This is the part that usually stumps people. If the sky is blue because of scattering, shouldn't the sunset be even bluer? To answer that, we have to look at the distance the light is traveling. During the middle of the day, the sun is directly above you. The sunlight only has to travel through a relatively thin slice of atmosphere to reach your eyes. It's a short trip, so even though some blue is scattering, plenty of it reaches you, making the sky look bright and vibrant. However, At sunset or sunrise, the sun is sitting at a very sharp angle on the horizon. This means the sunlight has to travel through a much, much thicker path of atmosphere to reach your eyes. By the time that light finally makes it to your face, the blue light has been scattered so many times that it is effectively scattered away entirely. It's been bounced around so much that none of it is left in the original beam. Only the long-wave, stubborn colors like red and orange, the waves that refuse to be scattered, are strong enough to survive that long, grueling journey through the thick air. When you see a red sunset, you are looking at the survivors of the light spectrum. Now let's get to the real mind blow, the part where your eyes and your brain are actually lying to you. If you look at the physics again, violet light has an even shorter wavelength than blue light. According to the mathematical rules of Rayleigh scattering, violet light should actually scatter more intensely than blue light. If we followed the physics strictly, the sky should be a bright, vivid purple. So why don't we see a purple sky? Why is it blue? It comes down to two major factors: the sun's output and your own biological hardware. First, the sun is a bit biased. It simply doesn't emit a balanced amount of every color. It puts out a massive amount of blue light but significantly less violet light. There are just fewer violet waves entering the game to begin with. Second, and most importantly, it's about how your eyes evolved. Human eyes are not objective scientific instruments. They are survival tools. Inside your eyes, you have color-detecting cells called cones. You have cones for red, green, and blue. Notice something missing? You don't have a violet cone. Your blue-sensitive cones are actually very efficient at picking up blue light, but they are much less sensitive to violet. When you look at the sky, your eyes are actually receiving a mix of scattered blue light and scattered violet light. But because your eyes are tuned to blue, and because there is more blue light coming from the sun, your brain does some auto-correcting. It effectively averages out the signal, ignores the violet background noise, and registers the final image as a nice, calm sky blue. If you were a bee or a butterfly, creatures that can see ultraviolet light, the sky would likely look like a completely different, much more purple world to you. So to summarize this cosmic mystery, the sky is blue because the sun is a hidden rainbow. The atmosphere is a giant filter that likes to play dodgeball with short waves, and your brain is a master of biological editing. We live inside a giant physical glitch where the atmosphere traps the blue light and tosses it around for our entertainment. It isn't just a color. It is the visual evidence of trillions of tiny collisions happening over your head every single microsecond. The next time you're sitting outside and someone asks you why the sky is blue, you don't have to give them the ocean reflection lie. You can tell them about Lord Rayleigh, the vibrating waves of the sun, and the secret purple sky that our eyes are too limited to see. It's a much cooler story, and it reminds us that even something as simple as the color of the day is actually a complex masterpiece of physics. Thanks for watching, and keep looking up.